Step into the fascinating world of celestial secrets and mind-bending discoveries as we unveil the extraordinary tale of the Compton Gamma Ray Observatory. Join us on a captivating journey through space and time where invisible cosmic bursts and explosive phenomena reign, pushing the boundaries of human knowledge. Get ready to witness the awe-inspiring power of the universe and unlock the enigmatic realm of gamma rays like never before. This is the untold story of the Compton Gamma Ray Observatory. Prepare to have your perception of the cosmos shattered. 20 years ago, in a desolate stretch of the Pacific, 2,400 miles, 3,900 kilometers, southeast of Hawaii, a spacecraft that opened our eyes to previously unseen cosmic sights ended its mission in a blaze of molten metal hitting the water. No one, save a military surveillance aircraft, was there on June 4, 2000, to witness the final throes of NASA's $670 million Compton Gamma Ray Observatory. So, after plummeting through Earth's atmosphere at breakneck speeds, the space telescope's surviving fragments sank forever to the oceanic depths. What was the Compton Gamma Ray Observatory? This unique spacecraft was named for Nobel laureate Arthur Holly Compton, 1892 to 1962, whose pioneering work in the 1920s demonstrated that electromagnetic radiation, or light, did not only take the form of a wave. Compton discovered that light also behaves like a particle, earning him the 1927 Nobel Prize in Physics. In addition, he also laid the cornerstone for modern high-energy physics, particularly related to gamma rays. These energetic particles extend from 10 keV to 10 MeV. 1 keV is 1,000 electron volts. 1 MeV is 1 million electron volts. And 1 GeV is 1 billion electron volts. And they originate from highly energetic sources like supernovae, pulsars, quasars, and black holes. On Earth, we are fortunate that our thick atmosphere shields us from their lethal onslaught. But that also means we can only study gamma rays with high-flying balloons and orbiting satellites. NASA's plans. NASA first unveiled plans to build a gamma ray observatory in 1977, but budget cuts threatened cancellation at every turn. And though Compton Observatory ultimately survived the axe, its launch was repeatedly delayed by technical difficulties. Built by TRW Incorporated, which was later acquired by Northrop Grumman in 2002, the space telescope tipped the scales at 35,000 pounds, 16,000 kilograms, making it one of the heaviest loads ever lifted into orbit by a space shuttle. And according to retired astronaut Jerry Ross, Compton's sturdy appearance reminded him of a stout diesel locomotive. The telescope covered a wide energy range, extending from 20 keV to 30 GeV, and would contribute to our understanding of the birth of the universe, offering unique insights into the existence of antimatter and probing the most exotic objects in the cosmos. An international team, including the United States, Netherlands, Germany, and the United Kingdom, built 4 powerful instruments whose remit extended from observing solar flares to pinpointing hypothetical black holes. One key focus of the telescope was spotting gamma ray bursts, or GRBs. These peculiar flashes of high-energy radiation pop like fireflies in seemingly random patches of the sky. Putting Compton in its place. Launched aboard the Space Shuttle Atlantis on April 5, 1991, Compton was placed in an orbit some 280 miles, 450 kilometers, above Earth's surface to avoid atmospheric drag and steer clear of the hazardous radiation in Earth's Van Allen belts. Astronaut Linda Godwin, using the shuttle's robotic arm, lifted the observatory out of the cargo bay before it deployed its solar panels. But then, its communications antenna refused to open. A thermal blanket had somehow gotten hung on a bolt. With the Hubble Space Telescope having suffered its problems in 1990, a failure on Compton was unthinkable. Efforts to jolt the antenna open were unsuccessful, forcing astronauts Ross and Jay Apt to go on an unplanned spacewalk to manually free it. And they did. Compton starts scanning the skies. The spacewalk's spectacular success set the stage for 9 years of remarkable discovery. Once it began its mission, Compton's Burst and Transient Source Experiment, BATSE, used 8 sensors at each corner of the spacecraft to offer wide-field viewing that could also triangulate the locations of GRBs. If it spotted one, then it would immediately alert other telescopes so that they could carry out detailed follow-up observations. Another instrument, the Imaging Compton Telescope (COMPTEL), mapped the celestial sphere with supreme precision. The Oriented Scintillation Spectrometer Experiment, OSSE, on the other hand, examined the spectral fingerprints of heavy elements in stellar nova and supernova. Finally, the Energetic Gamma Ray Experiment Telescope, EGRET, carried detectors 10 times more sensitive than any previous instrument, completing the first all-sky survey at energy ranges above 100 MeV and uncovering nearly 200 previously unidentified sources. Spectral range. Compton's spectral range, sensitivity, and resolution enabled it to detect 2,700 GRBs throughout its mission, which averages out to about 1 per day. But importantly, it also revealed the likely locations of these powerful bursts, revealing that they do not reside in our galaxy, but far beyond, indicating they put out a tremendous amount of energy. The Gamma Ray Telescope also uncovered fountains of antimatter streaming from the center of the Milky Way, perhaps ejected by our supermassive black hole, Sagittarius A*. It also showed the radioactive isotopes aluminium-26 and titanium-44 could be useful tracers for examining both ancient and relatively recent supernova. Compton discovered a new kind of active galactic nuclei, the blazar, and even witnessed intense gamma-ray flashes in Earth's atmosphere, which tended to localize above equatorial thunderstorms. But despite these triumphs, the observatory endured many bumps along the road. Both of its tape recorders malfunctioned in March 1992, and its hefty mass meant it tore through its limited supply of hydrazine fuel, which is used to keep its precarious orbit stable. Finally, in December 1999, one of its 3 stabilizing gyroscopes failed. As the curtains draw to a close on this captivating journey through the Compton Gamma Ray Observatory, we find ourselves standing on the precipice of knowledge, our hearts pulsating with awe and inspiration. The celestial ballet of gamma rays, the unveiling of cosmic mysteries, and the tireless pursuit of scientific discovery have left an indelible mark on our understanding of the universe. If you found our video informative, kindly subscribe to our channel so you won't miss out on our videos.